So hi everyone, and thank you for coming to this online conference. Today I'm talking about geodetic groups, and so the main sort of result of this talk is that geodetic groups are virtually free. And in fact, we kind of proved something stronger. It's true that quasi-transitive geodetic graphs are quasi-isometric to a tree. So like the proof goes through completely with graph theory sort of results. And so this is joint work with Murray Elder, Adam Piggott, Davide Spriano, and Giles Graham. Okay, so what is a geodetic graph? So in this talk, we're going to make sure that our graphs are locally finite, undirected, and simple connected graphs. And we're going to say a graph is geodetic if there is a unique geodesic between each pair of vertices. And so basic examples would be things like trees. So all trees are geodetic. Maybe odd length cycles are also geodetic. Complete graphs are also geodetic. Since there's a unique length one path between each vertex, but then something like an even cycle is not geodetic because you can take a path from this vertex to this vertex of length 2 and of length 2, and those are the shortest paths. So it's not unique. Okay. And so we're going to call a group geodetic, and we're focused on finitely presented groups if there exists a finite generating set such that the undirected Cayley graph of this group is geodetic. And so we're going to focus on infinite groups. And so in my example here, this is part of the Cayley graph of the free product of the cyclic group of order 2 and the cyclic group of order 3. And maybe I'll just write the generating set is AB and B inverse, where B is of order 3. And so you can see, like, if I take this vertex and this vertex here, then there is a unique shortest path from that to that. And so the reason I'm going to focus mostly on the geodetic, the infinite case, is because in the finite case, every finite group is geodetic, because you can always take the whole group minus the identity and get a complete graph for the geodetic group. Okay. Cool. And so, as I said, we're going to be focused more on the graph theory because everything comes through in graph theory correct as well. And so the graphs that we're going to be considering mostly are quasi-transitive graphs. And so I'll give the definition of that. It's kind of I guess it's the same as the co-compact from the previous talk. But so gamma is vertex transitive if there's exactly one orbit of the vertices under the action of the automorphism group. And so Cayley graphs are all vertex transitive. And then we've got this slightly less strong result that gamma is quasi-transitive if there's only finitely many orbits of the vertices under the automorphism group of gamma. And so I've got two examples here. The first one, this one here, is a quasi-transitive graph. And so we've got just bi-infinite ray, and then we've got these circuits of length 5 and 7 alternating. And you can check that there's finitely many orbits. But then if you have something where you've got a bi-infinite ray, and then propagating out from this central one, the circuits get bigger and bigger, then this is not quasi-transitive graph. Cool. Okay, so I'm going to give a brief history of geodetic graphs. So the first person probably to talk about geodetic graphs was Oystein Orr in 1962, and he posed the question of characterizing all the geodetic graphs. And he did this in the sort of the frame of generalizing trees, and he was probably more focused on finite graphs. It was kind of just like a question in his textbook, is whether they can characterize the geodetic graphs or not. Okay, and so we're going to be considering a few different types of groups in this talk. And so one of the groups that we're going to talk about is called the plane groups. And so these are the free products of finitely many finite groups and a free group of finite rank. And so in 1997, Shapiro asked, are the geodetic groups exactly the plane groups? So it's very easy to come up with. If you get given a plane group, I can quickly give you a generating set so that its Cayley graph is geodetic. And so we know that all plane groups are geodetic. And the way that you can do that is by you take the generators of the finite group parts, just take all of the elements as the generating set except for the identity, and then you just take the generator of the free group parts and its inverses, and that will give you a Cayley graph that's geodetic. And so one other result that is kind of important for this talk is that Papasoglu proved that if we start with a hyperbolic group and then we know it's geodetic, then it's virtually free. And so if you're not familiar with what these terms are, hyperbolic groups are the groups where the geodesic triangles are sort of thin, and so there's a bound on the distance between any side of the geodesic triangles from one to the other. And then virtually free, you can think about these as the groups that have a Cayley graph that is quasi-isometric to a tree. And so maybe just to give an idea of where we're at, so we've got finitely presented groups, which contain the hyperbolic groups. And then we have the virtually free groups. And then inside of those is the plane groups. And so this talk is going from finitely presented to virtually free. That basically, we already know if we've got hyperbolic groups, then we're virtually free. So really the step is going from finitely presented to hyperbolic. And our next talker in this seminar series, I think, is going to talk about some ideas we have for going from virtually free to plane. Okay, so let's go through the main results of our sort of preprint. So the first result is if gamma is a quasi-transitive geodetic graph, then gamma is quasi-isometric to a tree. So it's a tree up to some sort of like scaling and translation by some fixed amounts. And then from that, since the Cayley graphs of groups that are quasi-isometric to a tree are exactly those that are virtually free, we can get this sort of corollary that a geodetic group is automatically virtually free. We also have these sort of further properties, some of which were basically, or I would say they're kind of already known. If we knew that G was virtually free and geodetic, then we know that the centralizer of an infinite order element is exactly free group of rank 1, and then we also have this further result. So, and then if you're interested in rewriting systems, I'm sure they'll come up a little bit in the next talk, but a group G is geodetic if and only if G admits a presentation by a finite inverse closed confluent length reducing rewriting system. And so this is a nice little result for people that are interested in rewriting systems. Okay, so my objective of this talk is to kind of show you the proof of this main theorem here. So we're going to prove that quasi-transitive geodetic graphs are quasi-isometric to a tree. And so the motivation is from this idea of what properties of hyperbolic metric spaces have. So if we let M be a hyperbolic metric space, and we've got two different geodesic rays with perhaps different base points, we say that they're equivalent if the distance between them is bounded for all t. And so the way you can think of this is, well, you have your two geodesic rays, they travel along, but they're staying close to each other in some sense. And so this space is called the Gromov boundary. And so this is a very commonly sort of studied thing. Okay, and the actual motivation here that we got was that you can prove something is a hyperbolic group by understanding the space that the group is acting on. So suppose that M is a perfect metrizable compactum, so no isolated points. We can put a metric on it, and it's a Hausdorff compact space. Then if G, our group, acts by homeomorphisms on our space, such that it has these properties, then G is hyperbolic, and moreover, there's a homeomorphism of M onto this Gromov boundary of the group G. And by the Gromov boundary of G, I mean the we're thinking of the Cayley graph as our sort of our metric space. So this is our motivation. And so our idea was we feel like geodetic graphs will have at least some of these properties. Well, geodetic groups will have at least some of these properties. So we went about trying to recreate those. Okay. So if we have two different geodesic rays, and maybe they're different base points, then we're going to define a new equivalence relation. And this one's going to be useful in our geodetic setting. And we're going to say that alpha and beta are equivalent if there exists an S and T in the natural numbers, so that these paths eventually, these rays eventually meet and then travel together forever after. And so we're going to call the geodesic boundary of gamma the set of all of these equivalence classes of geodesic rays. And so here's an example of two geodesic rays that are the same element in our geodesic boundary. Okay, and so something that's pretty straightforward is if you have an element of our geodesic boundary and we fix some base point, then there's a unique representative, which we denote by the geodesic ray, the element of the boundary with its base point. And so there's a unique rep of this. And this is purely straight from the definition of geodetic. So there's a unique geodesic from one point to another in the graph. Okay. So we've got our definition of a geodesic boundary, and this works on any sort of graph that we've created. So we haven't put any assumptions. If we add the assumption geodetic, then we get this unique representative for each base point. And so the next thing we're going to do is going to define a topology on our geodesic boundary. And so we're going to say that two different geodesic rays, so these are not elements of the boundary, they're just representatives, they are coincide if they travel along for r steps and then possibly depart from each other. And so we're going to define a topology, and the topology is this idea that two geodesic rays, well, two elements of the boundary are considered close with respect to this base point O if they travel along together for a long time. So in our picture, we would say that alpha naught and beta naught are closer to each other than, say, beta naught and gamma naught, because, well, alpha naught and beta travel along together for longer. Okay, and so this topology, without even using the assumption that we are geodetic, we get that this topological space is Hausdorff. And then we also find that if we add in our assumption of geodetic, so we need to include geodetic in this proposition, then if you're given two different base points and you define the two different topologies based on those base points, then there's a homeomorphism from the geodesic boundaries under the identity map from these. So there's a homeomorphism between these two spaces under the identity map. So that's it's actually quite a tricky result to prove. And it's consistently using this sort of geodetic assumption. Okay. So now we've created this idea of a geodesic boundary. So this is like some sort of topological global properties of our geodetic graphs that we understand. And now we're going to think about isometrically embedded circuits. And so a circuit, of course, is a path where you have equal initial and terminal vertex. We say that the circuit's embedded if all the vertices are distinct except for the initial point and the end point. And then we're going to say that the circuit is isometrically embedded if every geodesic in the circuit is a geodesic in our larger graph. So you could think of these as like these sort of minimal types of circuits in the graph. And so we have this nice little lemma due to L.V. Price or Nebesky. I believe they definitely came up with it separately. But so if you have gamma to be a geodetic graph and you have two different geodesics, so they start at the same point and then they end one away, then they both have the same length. And if you add in this little gap between them, then this will be an isometrically embedded circuit. So you have two geodesics, alpha and beta, they end one apart, and then this is going to form an IEC. And so the idea of our proof is if we can bound these IECs, so say that there's no IECs of length greater than, say, 2n plus 1, then our proof will be done. And I'll give you the sort of the reasoning behind that now. So from a previous paper by Marielda and Adam Piggott, we generalized from this rewriting system stuff to just geodetic graphs. So let gamma be a geodetic graph and it has bounded IECs, then we know gamma has bounded non-degenerate geodesic triangles. And so by non-degenerate, I mean something like this is not allowed. So you can't have these sort of extra points. There has to be internally disjoint sort of sides to the triangle. And then if we consider the geodesic spanning tree of our graph, then we can prove that if gamma has bounded non-degenerate geodesic triangles, then it is quasi-isometric to a tree. And this is a very straightforward sort of proof, just using the definitions of quasi-isometric. And so, yeah, so our motivation is if we can bound IECs, then in our geodetic graphs, then we can prove that they're quasi-isometric to a tree. And so, yeah, the idea is we're going to combine our understanding of this sort of combinatorial data that IECs give us, and then this global properties of the topology of our geodetic graph from the geodesic boundary. Okay, so one of the structures that we have to consider in our geodetic graph, or in this proof, is an onion. And so all an onion is you start with like this geodesic by infinite geodesic array, and then as you move along, you have these IECs, and each IEC is disjoint from the other. And that's all that's written in this. And so as you can see, it kind of looks like or at least like half an onion. And so, and yeah, so it's continuing on forever. So we've got these unbounded IECs. And so the idea is we're going to prove that you can't have onions in a geodetic graph, or at least some types of geodetic graph. Okay, so our proposition is a geodetic graph cannot contain an onion. And we're going to let, for contradiction, we're going to let gamma be a geodetic graph that contains an onion. And so this proof, this is not the way we did it at first, but we realized that we had this nice trick that we could, instead of using some structure that we called lollipops, we instead have onions. But the idea is, so we attach a geodesic ray to the onion at the opposite end of each of the IECs. And we're going to call this new graph hat of gamma. And this new graph is also going to be a geodetic. So we've got our onion, and then so since every IEC has to have odd length because we're in a geodetic graph, then there's this opposite point to sort of this interval, and we're going to attach some sort of geodesic ray there. And then we're going to do the same for each one. And so we're going to consider a sequence of these geodesic rays. And these are all elements. If we can put them in the boundary of our new gamma, which is gamma hat. And so the idea of this proof is, well, if you start at S0, then the representative for this zeta I is along this path. But if we start at R0, then it's along this path. And it's the same for each case. So the geodesic from S1 or even from S0 would be something like this. And from R0 it will be something like this. And so we're going to consider sequences of our elements of the geodesic boundary. Okay, so first we'll start with if we consider it S0. And if we look at this sequence, then we'll notice that it's converging. And what does it converge to? If we start at S0, we go up, and we go up this way. And so we're getting closer and closer to this thing, this sort of path, S0, S1, Si, and so on. And so we're going to call this geodesic ray zeta S0, and it's the sequence of these vertices. And then if we start at R0 instead, then we have to go the other way, and we're going to get a sequence, a convergence in this direction here. Okay, and so we're in a Hausdorff space, so we know we have unique limits, and then we also know that since we have topologies and they're homeomorphic under the identity map, then we know that zeta and psi need to be equal. And so this will lead us to a contradiction. So that means that since these elements of the boundary are equal, then these need to be equivalent if we change the base point. So they need to end up meeting at some point at the end. But this is, well, simply not true, because if you look at the diagram, this thing's an onion and R0 is heading in the opposite direction of S0. So our two different limits of this sequence with respect to different base points are going different directions. And so we get a contradiction. So this proves that in a geodetic graph, we cannot contain an onion. Okay, and so the final part of this proof is we're going to finally use our assumption of quasi-transitive. So throughout this, we haven't used our assumption of quasi-transitive yet. But if we assume that gamma is quasi-transitive graph with unbounded IECs, then we know that gamma contains an onion. And so you'll notice also that this doesn't contain the assumption of geodetic. But so the way that you prove this is, well, we've got finitely many orbits and we've got unbounded IECs in some sort of locally finite graph. So if there's at least one of these orbits where there's infinitely many IECs. So we'll choose a vertex in that orbit and we've got all of these IECs. And since it's locally finite, then they must be bigger and bigger. So unbounded number and implies that there's an unbounded size. And then all we have to do is keep using this pigeonhole argument that since it's locally finite, we can choose the sequence so that they sort of agree for longer. So we've got things like this, and then we choose the next one to be the one that agrees for this step. And then we choose the next one to be the one that agrees for a step further. And so we build our onion just by using this sort of quasi-transitive graph assumption and our unbounded IECs. And so, yeah, this completes the proof, because if we're quasi-transitive graph with unbounded IECs, then we contain an onion. So if we're geodetic and quasi-transitive, we can't contain an onion. And so we have bounded IECs, and then so therefore we're quasi-isometric to a tree. Okay, so thank you for listening. I think that was a little bit rushed, but here are some references if you're interested. And yeah, I look forward to listening to Josh's talk where he talks about our ideas and sort of the motivations behind them of proving the next step in this geodetic group sort of proof.
Okay, thanks, Kane. Does anyone have any quick questions? Okay, I have one. Just since the proof relies heavily on these boundaries, are you able to talk a little bit about the relation that the boundary is defined on? Like, is it transitive, or like just to give some insight into how it gives the contradiction in the proof, really?
So the boundary, the main property that we're using with geodetic is this fact that it's independent of our base point choice. So if we choose some base point P, then we've got some topology, but we've got some space, and it turns out that this is homeomorphic under the identity map to the same space, but with a topology based on a different base point. And so this is important, and this really strongly uses this geodetic assumption. And so this is definitely not true if you aren't geodetic. And well, a nice result of our proof that a geodetic group is hyperbolic, let's say, is that this geodesic boundary that we've constructed is in fact the Gromov boundary from the previous slide.
Okay, great. Thanks. If there's no other questions, I'll give Kane a round of virtual applause. Thanks.